Hello Algebra 2. This video lesson is going to walk you through the basics of how to graph polynomials. I will get into more details later in the month, but for now this video lesson will give you all the information you're going to need for our next exam, and by the end of this you'll be able to draw pretty accurate, though rough, approximations of what a polynomials graph would look like. First of all, the lesson I'm going to tell you is going to be a blend of chapters 6.2 and 6.8. From 6.2 you've already learned some things, these 5 points here that I've grayed out and put in italics. And today I'm going to focus on these last 3 bullets: end behavior, the maximum number of intercepts, and the maximum number of turning points. First of all, end behavior. I've talked in class a couple of times now about this idea that you really ought to visualize and even memorize a 2x2 grid for yourself, where on one axis you've got degree, and the degree of the polynomial is either odd or even, and on the other axis you've got the leading coefficient, and the leading coefficient is either positive or negative. So in any corner of this you might have a positive odd, an even negative, an even positive, or so on. I've also gone on already to show you the end behavior that will happen with the polynomial in each of these 4 corners. You're going to need to memorize those end behaviors. So some of us find that by roughly sketching in the rudiments of what the pattern would look like between the beginning and end behavior helps us out. So an odd positive tends to be an upward or positive stair step or S shape. And an odd negative tends to be the upside down version of the same thing. There may be more than the number of bends that I've shown here between the beginning end and the final or to the right end, but the general shape holds true. Similarly, an even positive tends to roughly be a right side up U shape or smiley face, just as an even negative tends to be upside down. Now again, there may be more bends. This may look, instead of like a U, it may look more like a W, or even more bends than that. But the basic idea holds true. And this shouldn't be too surprising. Back in December and early January when we were talking about quadratics, we talked about the idea that quadratics are parabolas. Parabolas are U-shapes, and quadratics have an even degree after all. A quadratic always has its largest degree being 2. So we said that the positive quadratics are U-shapes and the negative quadratics are upside down. And that next step beyond a quadratic, the third degree, instead of having the exact same end behavior, it instead has starts low, ends high, or the opposite, starts high, ends low. Enough of that, you're going to have to memorize it. I'm going to, this is the way the textbook explains the same picture that I've just shown you. I'm going to suggest that you come into class and ask me about this, and I can go into more detail about this, but it's not going to be something I'll be able to cover in this video. So, let's practice this. First of all, I'll do 15 and 16. Well, first of all, 15. The degree is 1 because there's a 1 on the x here and there is no variable over here. So the degree is an odd number. 1 is, after all, an odd number. The lead coefficient on that term is that -5. So it's a negative odd. So 15 belongs down here in the negative odd quadrant. 16. The degree is 4. Because that's the largest exponent on any x, and its lead coefficient, 3/5, is a positive number. It may be less than 1, but it's a positive number. So this is a positive even, which means that 16 belongs here, and its general shape for 16 is, roughly speaking, going to be either a right side up U, a right side up W, or something similar to that general idea. All right, hit the pause button. I want you to do the same for 18, 23, and 25. When you come back, I'll tell you what the right answers are for those shapes. Okay, I'm going to assume that you did that, and here are those answers. 18 and 23 are both positive evens, while 25 is a positive odd. Perhaps the hardest of these was 18. The degree is 2. That shouldn't have been terribly difficult for you to realize. But the lead coefficient on that term is radical 2. Even though the radical 2 comes after the x squared, it is still modifying that x squared. Radical 2 is a positive number. It's something between 1 and 4. So it is a positive even, and that's why 18 belongs in this quadrant. Moving on, I also said that important things for you to know from chapter 6.2 are these notions about maximum number of intercepts and turning points. The maximum number of intercepts is going to be exactly the same as the degree. Note that this has the maximum possible number. So it may be that there are fewer intercepts than the degree, but there will never be more. The maximum number of turning points, in other words, the maximum number of bends in the graph, is always going to be one less than the degree. Again, this is a possible maximum, but there could be fewer, and we'll talk about those examples as we go forward. So let's make sure that you recognize what the maximum possible number of turning points are for a couple of these. Picking out number 16, I'll do that one. The degree is 4. So the maximum possible number of bends, or turning points, would be 3. I'd like you to do the same thing for the same ones that I had you do before, 18, 23, and 25. Tell me what the maximum number of turning points is. Hit the pause button. When you come back, I'll tell you the answer. Okay, I'm going to assume that you did that. We said already that the degree for 18 is 2, so the maximum number of bends or turning points would be 1. For 23, we said that the degree was 4, the maximum number of bends would be 3. For 25, same thing, the degree is 3, so the maximum number of bends is 2. Okay, maximum number of intercepts. Like I said, it's the same as the degree. But the problem that we have at this point is that we don't know enough from chapter 6.2 about how to find intercepts. That's why I skip us ahead to chapter 6.8. In 6.8, we are given what the intercepts are. In between chapter 6.2, actually in between chapter 6.3 and 6.8, are a number of steps that teach us how to find intercepts. I'm going to fast forward and take advantage of the information they give you in 6.8 and show you what you can do when you know what those intercepts are. So in 6.8, they give this information to you. How are they telling you what the intercepts are here in this function right here? Well, as it says here, the since x plus 2 and x minus 1 are factors of f of x, negative 2 is an x-intercept and 1 is an x-intercept. How do we know that? Well, look at it this way. I could have called f of x y. I've said that a number of times this year. Now look at a graph. In order for me to plot an intercept, an x-intercept that is, it has to be on the x line, the x-axis. Anything on the x-axis has a y value of 0, right? It has 0 height. So instead of y, I put in 0 whenever I'm talking about an x-intercept. The only way I'm going to get a calculation of 0 here is if either this binomial turned out to be 0 or this binomial turned out to be 0. Well, the only way that could happen is if x is either negative 2 or x is 1. 1 minus 1 makes 0 after all, and negative 2 plus 2 makes 0. So that's why they say the x-intercepts of the function they've given under the handwriting I've made here are negative 2 and 1. And you can go ahead and plot them if you want to. There they are, those x-intercepts for that graph. Let's practice this. 17, 21, and 22. Tell me, please, what the x-intercepts are for each of those. Okay, I'm going to assume that you did that. For 17, the x-intercepts are 3, negative 4, and negative 1. Why? Because 3 minus 3 makes 0. negative 4, plus 4 makes 0, and negative 1 plus 1 makes 0. That's why essentially all you're having to do is reverse the sign on the number inside the parens, unless there's any kind of coefficient inside here, and so far there hasn't been. 21 and 22, quickly, there are the answers. Those are the x-intercepts. I can tell you more, though, just by looking at this equation, and soon you'll be able to tell me more than just the x-intercepts. I can tell you the degree. The degree for 17 is 3. Why? Because there are 3 instances of x. 1, 2, 3. And similarly for 21, the degree is 4, because there are actually 2 instances of x here, because it's squared. So 2, 3, 4 is the degree for 21. Hit the pause button and tell me what the degree is for question 22. Okay, I'm going to assume that you figured that out, and the degree for 22 is 5. I can also tell you the lead coefficient for number 17. The lead coefficient is 1. Why? Because there is no other coefficient represented here outside the parentheses, so it must be 1. Quickly tell me what the lead coefficients are for 21 and 22. Okay, here's the answer for those. Both of those also have a lead coefficient of 1. In fact, I think all of the examples in this practice slide here have an LC of 1. All right, now that I know the lead coefficient and the degree, I can, as you know, talk about end behavior. So for example, for 17, the end behavior is starts low, ends high. I can also plot those x-intercepts. 3, negative 1, and negative 4. So go ahead, do the same thing for 21 and 22. Okay, I'm going to assume that you did that. Here are the rough representations of 21 and 22. Now we can actually go even beyond this and fill in the information in between the end behavior arrows. Let me show you one other thing, though, that I have to teach you in order to do that. There is one paragraph buried in chapter 6.7 that I wish were more highlighted. I wish it got one of those green boxes that the chapter sometimes gives to key information. I think this is key information. When a factor, when a binomial, when a polynomial has been factored, when one of those factors, they just generally call it x minus k. Looking back here, they're talking about an example like this, x minus 3. When that thing has an odd power, so in other words, this x minus 3 did have an odd power, its power was 1, whereas x plus 1 has an even power, its power is 2. Oops. When it has an odd power, the graph is going to cross through the x-axis. But when it has an even power, the graph is, well, the textbook says tangent. The graph is going to bounce off the x-axis, essentially. And I'm going to show you what I mean. Remember, this is where I left off. Now, I'd said for 17, the degree on that is 1, as is that. That's also 1. And the degree on that is also 1. Similarly, over here, the degree on this binomial is 2, or even, in other words, and the degree on this one is 1, or odd. So each of these has an odd degree. That means in each of these, at each of these intercepts, at each of these x-intercepts, the line is going to pierce through, go straight through the x-axis. So I start drawing it. It goes through the negative 4. It has to bend around to get back to the negative 1, so it does, but it's going to go through the negative 1. Whoops, sorry. And then it has to bend around again to get back to the 3, but it's going to go through that 3. At this point, I'm going to pause. I'm going to stop this video. I can see I'm going to need about 2 more minutes, but I'm going to run out of time technically. So I'm going to stop this video here and make a very short video to finish this lesson off.